We will spend the rest of this chapter looking at some very important molecules and compounds. We can group these into two categories, inorganic and organic. Inorganic compounds or molecules generally do not contain carbon and hydrogen as principal structural elements. That doesn't mean they cannot have carbon or hydrogen, it just won't be as much as you would see in an organic compound. Also, inorganic compounds or molecules tend to be very small compared to organic ones. Examples of inorganic compounds or molecules include oxygen, water, carbon dioxide, and things we classify as acids, bases, or salts. Organic molecules or compounds are always made from carbon and hydrogen. They are also relatively large molecules and include things such as carbohydrates, lipids, proteins, and nucleic acids. We are going to start with the inorganic molecules. Water is the most important molecule in your body. It is required for all normal physiological functions. Water is so important that 70% of your body mass is water. It helps to maintain the solubility of inorganic and organic molecules in your body. It's important for many chemical reactions. It is involved in lubrication, such as the fluid that is found within your joints, and it is important for the maintenance of body temperature. Water is so important that you can only survive a few days without water, but depending on how much fat is stored in your body, you can go weeks or months without food. Let's look at acids, bases, and salts. Acids are compounds that dissociate in water and release hydrogen ions. When you put a strong acid in water, the acid will dissociate completely in the water. Hydrochloric acid is a very strong acid, so when you put it in water, it dissociates to form hydrogen ions and chloride ions. The hydrogen ion is considered a proton, so acids are often referred to as proton donors, which means they release protons in water. This becomes important when we talk about buffers a little later. Now, weak acids do not dissociate completely. Carbonic acid, H2CO3, is a weak acid. When you put it in water, it reaches an equilibrium between the amount of hydrogen ions and bicarbonate ions, which is HCO3. Bases are molecules that dissociate in water and release a hydroxyl group, or OH. They can also remove hydrogen ions from water, so they are sometimes referred to as a proton acceptor. Again, this becomes important when we talk about buffers in a little bit. Just like strong acids, strong bases will also dissociate completely in water. For example, sodium hydroxide will dissociate into sodium and hydroxyl groups when put in water. The hydroxyl, or OH negative, is the proton acceptor. Salts are molecules that dissociate in water into a cation and anion. Neither of these are hydrogen or hydroxyl. So for example, if you put sodium chloride into water, you get sodium ions and chloride ions. pH is a measurement of the hydrogen ion concentration of a fluid. It is based on a logarithmic scale. When we look at water, the number of hydrogen ions is written as 0.0000001 moles per liter. If we were to write this in scientific notation, it would be 1 times 10 to the minus 7th. This is minus 7 because we count backward from the decimal point 7 places. So something that has a neutral pH contains a concentration of hydrogen ions of 1 times 10 to the negative 7th moles per liter. If the concentration of hydrogen ions is 1 times 10 to the minus 7th moles per liter, we can rewrite this as the negative log of 1 times 10 to the minus 7, which equals 7. This is how we get the pH number. Okay, so let's look at the end of the pH scale where things are considered highly acidic. When we have a solution of a pH of 1, what that really means is that the concentration of hydrogen ions is 0.1 moles per liter. Likewise, if we have a pH of 2, the concentration of hydrogen ions is 0.01 moles per liter, and so on. The items that are considered highly acidic have a high concentration of hydrogen ions. So let's now look at the other end of the pH scale where we have the very alkaline solutions or basic solutions. when we have a solution with a pH of 4. That means the solution of hydrogen ions contains hydrogen ions at a concentration of 0.0000000000001 moles per liter. That's 13 zeros and then 1. This is much lower concentration of hydrogen ions than something that has a pH of 1. Solutions with a very high pH have a much lower concentration of hydrogen ions. Acidic solutions have an increasing concentration of hydrogen ions, whereas alkaline or basic solutions have a decreasing concentration of hydrogen ions. So what is a normal blood pH? It is 7.35 to 7.45. pH maintenance is really important for homeostasis. We will learn a lot more about exactly how your body maintains pH in A&P2. For now, let's just talk about what a buffer is and what it does. A buffer is a compound that helps to maintain the pH of the body fluids by either removing or replacing hydrogen ions. Usually this involves an acid and base pair. For example, when hydrochloric acid, a very strong acid, is mixed with sodium hydroxide, a very strong base, we get sodium chloride and water, or salt water, which is a neutral solution. This works because the hydroxyl in the sodium hydroxide combines with the hydrogen in the hydrochloric acid to form water, while the sodium in the sodium hydroxide and the chloride in the hydrochloric acid combine to form sodium chloride. This is a dramatic example, but clearly demonstrates how sodium hydroxide is the acceptor of a proton or hydrogen ion from hydrochloric acid.